Yes, your questions first. So if you remember the last time we were studying, we were looking at the time evolution. We had described this time evolution operator U, which what it does is if you take a state at the time t0, it is in the state alpha, and applied with this time evolution operator, t1, t0, it just evolves it to the time t1. t0 at the time t1. So this is how we define the time evolution. And furthermore, by studying the properties, we had seen that it is unitary. And if you have two time evolutions, first from t0 to t1 and then from t1 to t2, this is basically a single time evolution from t0 to t2. And we said that u, we can write it in the form 1 t1 t0, 1 minus I over h bar h of t, t1 minus t0. Of course, this is if h is independent of time. And then we evolved how states evolve. So what we had seen is if alpha I, ai, the kets ai are just an eigenket of this Hamiltonian. Well, they are eigenkets of A, which commutes with Hamiltonian. And if the spectrum of A is non-degenerate, then we already know that these AIs are also eigenstates of the Hamiltonian. And if you have any ket at the time t0, if you expand it in terms of these kets AI, Ci being the expansion coefficients, then at the time t, our ket evolves to Ci e to power minus I over h bar EAI t minus t0 AI. So basically, each one of these energy eigenkets, they acquire this phase. The phase itself doesn't change the probability if it was just a single ket, but nevertheless, if there is a superposition, it basically changes the possible interference terms in the state. And if you look at the energy expectation value of any operator B in this state, we said that this is basically the time dependence at the time t. This is given by Ci star Cj e to power minus I over h bar EAI minus EAJ AI B AJ. So it depends on time and it's basically a sum of terms that are oscillating with frequency related to the energy difference. So this energy difference divided by h bar is just some kind of a frequency. So it's a superposition of terms that are oscillating with those frequencies. And that was basically what we had done more or less on Wednesday. So any questions on these? So we also studied how the spin changes with time. If you remember, we had started with a state that was polarized in the x direction, and then we looked at how the expectation value of Sx and Sy changes, and we observed this precision of the spin. Now, any questions? Now, today we will do a similar example, the neutrino oscillations. You see, for the time being, we are not talking about any differential equations, we are not solving any complicated equation with special functions, etc. But nevertheless, we can still make some predictions. So if you look at in your book, there is a measurement of this spin precision. Now we can study with our knowledge up to this point, we can even study neutrino oscillations. And these neutrino oscillations are also observed experimentally, and we can predict them theoretically. Now, have you heard of neutrino oscillations? Have you heard of neutrinos? Okay, so they are kind of weird particles in the sense that they almost do not interact with anything. They very rarely interact, and every second there are millions of them passing through your body, for example, from the sun, and you don't feel it. They just go through Earth, through the diameter of the Earth, as if there was nothing there. But from time to time they can interact, and when we can detect them in the few cases that they interact. So the first observation of the first prediction of the neutrinos were due to Fermi. What they did was they looked at the energy spectrum of beta decay. So basically in beta decay what you have is you have an initial nucleus, and the initial nucleus decays into a final nucleus and an electron. That was the only things that were observed. But if you have one particle decaying into two particles, and if you want to conserve both energy and momentum, the energy of the final states are fixed. So the electron should have a single energy, if this were the case. But what we observe in the energy spectrum of the beta, the energy, these are the number of beta particles having that given energy. Basically, we had a spectrum. So this was expectation if no neutrinos. And this is what we have seen. So more something like this. So we had two options. Either we should give up the fact that energy is conserved. So apparently there was no energy conservation. Or what Fermi did was he speculated that there was some other particle that we do not observe. And it turned out that I think at least 10 years later we actually could observe the neutrinos. And our observations first told us that there were 3 different kinds of neutrinos. And the kinds are basically defined by with what particles they interact. For example, neutrinos interacting with electrons only, they are called electron neutrinos. And there are neutrinos who interact with muons only, they are called the muon neutrinos. And later on we observed neutrinos that interact with tau only, with the tau lepton. So those are what we call the tau neutrinos. Now in our simple model of today, we will just be dealing with these two. And so we knew about these neutrinos. We had certain problems though with neutrinos. For example, we have a good model of the sun. And in sun, we know how much neutrinos should be produced. And then we could measure how much neutrinos arrives on Earth. And it turns out that the electron neutrinos that are produced in the sun, very few of them arrive. 1/3 of what we expect arrives on Earth. So that is what we call the solar neutrino problem. This was one problem we had with neutrinos. We have a very good model of the sun which predicts most of the properties of the sun, but it also predicts how much neutrino should be arriving on Earth, how much electron neutrino should be arriving on Earth, let's say. And when we measure them, we didn't observe enough. And then there is also what we call the atmospheric neutrino problem, which was basically, this is Earth, so it has an atmosphere. There are many cosmic rays hitting the atmosphere. And when they hit one of the particles that are produced in abundance is what we call pions. While pions dominantly decay into muons and muon neutrino, and muons, they decay into electrons and electron neutrino. So basically what happens is the pion eventually decays into an electron or a positron with and also muon neutrino, with a electron neutrino and 2 muon neutrinos. One is an antineutrino, but that doesn't really make too much of a difference. So what we expected to observe on Earth was the number of electron neutrinos to the number of muon neutrinos, counting both neutrinos and antineutrinos. We expected this number to be around 1/2. Of course, there are other sources of electron neutrinos and muon neutrinos, but most of them, the majority of them, come from the decays of the pions. So we would expect this ratio to be something around 1/2. This is expected. What we observed was 1. This is what is measured. So this was basically our problem, that the some of the neutrinos, at least, that we are measuring on the surface of the Earth doesn't match with our expectations. So they kind of change. Now that was one explanation of why we don't observe as much neutrinos as we wanted to. One is, for example, look at the spin. The spin just changes in time, or we had seen that in time evolution of states. If the initial state is not an energy eigenkette, look at just here, if the initial state is not an energy eigenkette, in that case, it just changes on its own. You don't need to do anything. For example, we looked at the case of a spin in a magnetic field. If the initial spin was aligned in the x direction, that is not an energy eigenkette. So with time, it changes to a state with spin in the y direction or spin in the minus x direction. That is what we mean by precession. So that was one possible explanation of this discrepancy. So it might be that one kind of neutrino is changing into some other kind of neutrino. So that was the expectation, let's say. Now there's one prediction already if you just hypothesize such a scenario for these explanations, at least for the solar neutrino problem. Well, this is the atmospheric neutrino problem. Now, if the neutrinos are changing as they are coming on Earth, well, the number of electron neutrinos will be changing, number of muon neutrinos will be changing. So you don't really get this 1/2. But the total number of neutrinos should be the same. Or the same holds for the solar neutrino. If you know how much electron neutrino is produced, okay, they will not be arriving on Earth as electron neutrinos. But if they are not arriving as electron neutrinos, they will be arriving as some other kind of neutrinos, because as far as we know, neutrinos are stable. They don't transform into other types of particles. They stay as neutrinos. So the total number of neutrinos should be what is predicted by the solar standard model. And when we actually made the experiment, that is what we observed. The number of total neutrinos that's coming from the sun is equal to the number of neutrinos, electron neutrinos that we are expecting from the sun. But the number of electron neutrinos is less than what we are expecting. So that's our explanation, is that now, okay, they start out as electron neutrinos, but when they reach here, they don't stay as electron neutrinos. So this is only possible if electron neutrinos is not an energy eigenstate. Electron neutrino and similarly the muon neutrino. They are not energy eigenkettes. They don't have a definite energy. But what we can have is, these are what we call flavor bases. Still, electron neutrino only interacts with electron, muon neutrino only interacts with muon. But these muons do not have a definite energy. States that have definite energy, we will call them nu1 and nu2. So nu-e, the electron neutrino, is some superposition of these two states. And nu-mu is some other combination, the orthogonal combination. Now let's see how they will change in time. What is the probability that a neutrino that starts out as an electron neutrino, it will stay as an electron neutrino in time? So let's say that at nu-e at t is equal to 0. Now let me write it in this way. We have a state at t is equal to, let me say 0, is given by nu-e. Of course, it will evolve in time. At the time t, it will be a different state. If we want to talk about the probability that it is still an electron, we should look at the coefficient of nu e in this nu ket. This is the amplitude, and then we need to take the square of this thing. This is the probability that nu e stays as nu e. Or we can do a similar thing. We start as a nu e at time t equal to 0. We let it evolve. And what is the probability that it becomes a muon neutrino after traveling some distance? This is called the probability for conversion. Now let's try to calculate these probabilities. Now, any questions up to this point? This is what basically the overview of what we will be doing. So we have then, we have some bases to describe our neutrinos. These are not energy bases. These are what we create in reactions in the sun. These are what we create. We basically create this one. But since it's not an energy ket, energy eigenket, we can write it in terms of the energy eigenkets. But since it's not an energy eigenket, it's not a stationary state. It will be changing in time. So our question is, how does it change? So let's assume that for simplicity, I will just assume that we create some neutrinos having definite momentum. So this alpha at t, an arbitrary time, this will be, you see, initially it was cosine theta, nu1 plus sine theta, nu2. Nu1 and nu2 being energy eigenkets. Well, we know how a given ket, which is expressed in terms of energy eigenkets, evolves in time. So basically, each one of these components will acquire a phase, h bar e1 t, e to power minus I over h bar e2 of t. So this is my ket at the time t. Each one of the components takes these phases. Now, what is the energy if the state is a definite momentum state? Ai is nothing but square root of p squared, the momentum squared, plus m squared c squared. Now c to the 4, this is c squared. This is the energy of my ket. Now you see, in the neutrinos, until the beginning, until the 2000s or the end of 1900s, we thought that they were just massless. And the standard model, the neutrino discovery of the neutrino is something like 1950s. And until the end of 1900s, for more than 30 years, let's say, we thought that they were massless. Basically, the mass they have was beyond the limit of our measurement. We could measure the mass of the electron, we could measure the mass of other particles, but the mass of the electron was smaller than our sensitivity. So that basically tells us that if they have a mass, and it in fact turns out that they have a mass, the mass is very small. Well, if the mass is very small, in general this will be a very small number compared to this one. So I can basically make a Taylor expansion. So this will be equal to Pc times 1 plus mi squared c squared over p squared to the power 1/2. Or this is more or less Pc times 1 plus mi squared c squared over 2p squared. Plus mi squared c cubed divided by 2p. This is the energy of the ith neutrino. let's keep this in mind. Now let's try to calculate these probabilities. What's the probability that an electron neutrino stays as an electron neutrino? Remember, this was nu E, this inner product squared. Well, nu E, you see this is the expression of the electron neutrino. Cosine theta nu 1 plus sine theta nu 2 multiplied with cosine theta e to power minus I over h bar E1 t nu 1 plus sine theta e to power minus I over h bar E2 t nu 2. Well, we just take the inner products. You see, this times this is just 1. This nu 1 times nu 2 is 0. Nu 2 times nu 1 is 0. Nu 2 times nu 2 is 1. They are the eigenkets corresponding to a Hermitian operator with different eigenvalues. So they have nu 1 and nu 2, they are orthogonal to each other. So this is equal to absolute value of cosine squared theta e to power minus I over h bar E1 of t plus sine squared theta e to power minus I over h bar E2 of t. This is, we need to calculate the probability, we have to take the absolute square of this number. Or let me write it in a slightly different form. This is cosine squared theta plus sine squared theta e to the power I over h bar minus I over h bar E2 minus E1 t squared. So basically I just multiplied this complex number by e to the power I over h bar E1 t. The number I multiply has a unit norm, so it doesn't change the norm of that number. And the absolute value squared of a number is the real part squared plus the imaginary part squared. So this is the real part is cosine squared theta plus sine squared theta sine of delta E over h bar t. Now cosine. All of this squared plus sine squared theta sine of delta E over h bar t, all of this thing squared. This is the probability that an electron neutrino stays as an electron. This is the real part squared, this is the imaginary part of that number squared. Well, let us open up the parentheses. This is cosine to the 4 theta plus sine to the 4 theta plus twice sine squared, cosine squared, sine squared theta, cosine squared theta, and cosine delta E over h bar t. Well, if theta is just a constant, it is a constant that relates how the nu e and nu mu are related to nu 1 and nu 2. This is a constant, it doesn't change with time. But you see here you have an oscillating term which changes with time. So let's see, what is this delta E? Now delta E, well, by definition it's just E2 minus E1. Well, E2 and E1, they just differ by this mass over here. This PC is the same. So this is equal to delta M squared C cubed over 2P and T let's say we can relate the time to the distance the neutrinos cover. T should be L over V, or well, let's just keep it L over V. What's the velocity of a relativistic particle? Well, its velocity is more or less c. So it has a high energy compared to its mass. The mass is very small, so it will be more or less moving at the speed of light c. So this delta E over h bar t is delta m squared c cubed over 2p times L over c squared. Well, this is equal to delta m squared L over twice E over c. Approximately. P is almost E. Now, these are the reason why I converted it into E is easier to measure. So P nu E to nu E is just A plus B times cosine delta m squared c cubed L over 2E. And you can calculate the probability that nu E goes to nu mu. Can you guess the probability for this one? Well, that is, well, you see, we have nu 1. We have this state. Nu 1 and nu 2. We are assuming for simplicity that the neutrinos have the same momentum. We are creating a neutrino state with a definite momentum. Well, since these have a definite energy, nu 1 and nu 2, that means they have a definite mass. You see, energy squared minus p squared c squared divided by c to the 4, this is m squared. So we are talking about states that have a definite momentum. If they also have a definite energy, then they have a definite mass. Nu 1 and nu 2, they have a definite masses. It can be different, I don't know. We don't know yet. Yeah, now we know. The experiment tells us that the masses are different. Nu E and nu mu, they are not states that have a definite energy. Since they don't have a definite energy, they cannot have a definite mass. Now the question is, nu 1 and nu 2, do they have a different mass or do they have the same mass? And the answer is basically over here. If we can measure this probability, that is what we had measured. If neutrinos, they all have the same mass, then this term is 0. And this probability will be just, well, delta m squared is 0. And this term over here will be just a constant. In fact, it turns out to be 1. Let me write it in a slightly different form. Let me add a minus 1 over here. It should have this form. If the mass differences are 0, if they all have the same mass, their mass differences will be 0. So this term is 1. 1 minus 1 is 0. So the probability that the electron neutrino will stay as an electron neutrino will be definitely 1. And the probability that an electron neutrino will be converted into a muon neutrino, well, let me make one more change. This is minus plus. It stays the same. It stays the same. You see, here we are talking about an electron neutrino to stay an electron neutrino. There is no, if delta m squared is 0, then there shouldn't be any oscillation. If delta m squared is 0, then there is no oscillation. If there is oscillation, there is delta m squared cannot be 0. And the other probability is just b times 1 minus cosine delta m squared c cubed L over 2e. So to say whether the neutrinos they all have the same mass or they all have different masses, we can just look at these probabilities. If we can measure those probabilities, and if we measure that these probabilities this is not 1, and furthermore, I mean, you can just plot the spectrum with respect to energy or L. If you can see that they oscillate with distance from the source of the neutrino, then you can even determine what delta m squared is by just looking at the oscillation frequency as a function of L. So let me see. Not that one. Okay, if you just look up in your book, you will see how these probabilities change with distance. So this is the observation. It's as a function of L over E. So if you plot these probabilities as a function of L over E, you should see some oscillating terms, and those oscillations, their frequency is determined by the mass squared differences in the mass squared of the neutrinos. So experiment definitely tells us that there are oscillations, and hence we definitely know that these delta m squares cannot be, they are different than 0. So we still don't know what the mass of the neutrinos are, but we know that their masses are different. So at most, one of them can be 0. Yes?
Kütle farklısı nasıl aynı partikül diyebiliriz? Bir de şöyle bir soru sorayım. Kütlelerin eğimi farklı olmasının nedeni hızların farklı olmasından kaynaklanıyor. Yani kütlenin gravitesi bir şey mi geliyor, nasıl bir şey mi geliyor? Sonra hızları aynı mı?
Well, let's see. Are you a human being? Are you human? Is Kaan a human? But you have different masses, right? Well, you see, we are calling them groups of particles. Neutrinos is one group of particles. For example, we call hadrons. Hadrons are the name of the group that interacts with a strong force. They all have different masses. Pion is a hadron, proton is a hadron, neutron is a hadron. They have different names. Of course, if we have particles that have almost the same mass, then we tend to give them the same name. For example, we have 3 different pions. They all have a different name. They all have the same name, sorry. They have different charges, but nevertheless we call them with the same name because they have very similar properties, except on the charge and very slight variation in the mass. So we have here these 3 particles, nu e, nu mu, and nu tau. They are very similar to each other. They have 0 electric charge. They are all spin 1/2. They don't feel strong interactions. They are electrically neutral, and they have almost the same mass. So that's why, since they have very similar properties, we just give them the same name, neutrino. But they have different properties also. They are not identical particles. We know that one of them is interacting with electrons only, one of them is interacting with muons only, one of them is interacting with taus only. So although we are calling them neutrinos, they are different particles. They are not the same particle. And it also turns out that these kets do not even have a definite mass. I'm not saying that they have different masses. They don't have a mass. The concept of mass does not apply to these particles. Just similarly, if you are talking about a particle that has a spin in the z direction, You cannot say that its spin in the x direction has this value. That concept doesn't make any sense. Just like that, if you are talking about the electron neutrino, and the way we define the electron neutrino is a neutrino that interacts only with the electron, this observation is not compatible with the observation of mass. So that's basically what we are saying in the terminology of quantum mechanics. The flavor, so-called, I mean, these types, electron, muon, or tau, is, in the particle physics terminology, those are what we call flavors. Flavor observation and mass observation, they are not compatible. You either talk about the flavor or you talk about the mass. So these nu e, nu mu, and nu tau, they don't have different masses, they don't have the same mass. It just doesn't make sense to talk about the mass of these. If you want to talk about the mass, you cannot talk about the flavor. You can talk, these states, they have a definite mass. They are still called neutrinos because they are fundamental particles with fundamental fermions that only feel weak interaction. That is how we define a neutrino. They are still neutrinos. This nu1 interacts both with electron and also with muon. So it's not an electron neutrino, it's not a muon neutrino, but it has a definite mass, this nu1 state. Similarly, the nu2 state has a definite mass. And since nu1 and nu2, they have a definite mass, and we also know the Einstein's energy, momentum, and mass relation, if you create a nu1 state with a definite momentum, then it is a state of definite energy, because mass is known, it has a mass, its momentum is known, so it has an energy. But for the electron neutrino, well, this relation doesn't make any sense because there is no mass of the electron neutrino. By the way, I'm not saying, when I'm saying that the electron neutrino has no mass, I'm not saying that it has mass 0. It just doesn't make sense to talk about the mass property of the electron neutrino. There is no such property that we can use for the electron neutrino. And again, these are observed. I mean, your book is probably going around. You have seen, we have observed this phenomenon.
Şöyle diyebilirler miydi? Yani bunları başka bir state'e çeviren şey o zaman atıyorum bir mass operatörü değil de bir rotation operatörü gibi bir şey. Biz bunun ne olduğunu bilmiyoruz ama sonuçta enerjinin şeyiyle operatörle yani Hamiltonian'la şey yapmıyor, commute etmiyor. Daha sonra bu relativistik yaklaşımdan dolayı mı ancak yani mass'le ilgili bir şey vardır. Bu o yüzden oscillate ediyordu.
Well, before the 90s, I don't really know the exact history. I don't think we knew that they changed. We didn't know that. We couldn't measure them even precisely enough to see whether they changed or not. Well, when we did discover that they were changing, there were many models. This wasn't the only model to explain this change. One model, for example, was that maybe the neutrinos have a magnetic dipole moment. If they have a magnetic dipole moment, magnetic field would rotate their direction, the direction of the spin. Well, neutrinos are, okay, let's not go into too much details, but if they change the direction of their spin, they stop interacting with anything. So, for example, in this model, what was said that, okay, the electron neutrinos were created, they all arrive on Sun, they all arrive on Earth, but on Earth when they arrive, some of them are just converted into a neutrino which cannot be observed at all. So that's why we are not observing them. So there were these two models made two different predictions. One predicted that, okay, all the neutrinos are arriving here, but they are just of different type, not necessarily electron neutrinos. So the prediction of this model is that if you just can detect all types of neutrinos, electron, muon, and tau, then the total sum should be equal to the number of neutrinos that is expected from the sun. The other model, on the other hand, said that, okay, we don't need this oscillation. Electron neutrinos, they start from the sun, but in the magnetic field of the sun, their direction of the spin changes, and hence they stop interacting with anything. And when they come on Earth, we only detect the ones that are still detectable, the electron neutrino that interacts with something. So in this new model, in this other model, if we just measure all the electron, muon, and tau neutrinos, their number should still be much less than what is predicted to come from the sun. So we have these two models that make predictions. Until that time, at least, we were only measuring the electron neutrinos coming from the sun. And both of these models predict that the electron neutrinos coming from the sun should be less than what is produced in the sun. But one model says that if you count all of them, it should be equal to the number of neutrinos produced in the sun. And then we have prediction. We tested it. It turned out that the total number of neutrinos that is coming from the sun is equal to the number of electron neutrinos that we predict is observed in the sun, is created in the sun. So the second model is dead, let's say.
O zaman sorum şöyle gelir mi hocam? Burada dediğim gibi Hamiltonian'ın o bunu değiştiren, nötronları değiştiren operatörle komut etmemesinin sebebi aslında relativistik ve non-relativistik kuantum mekanik arasında bir geçiş mi olur?
Not really. I mean, you see, the only reason why I'm using this relation is that I want to find some expression for the energy of the neutrino in terms of its momentum and velocity. That's the only reason why I'm using it, not because it's relativistic. Well, of course, the neutrinos, they behave relativistically, but the fact that they are moving relativistically is not really that important in this case. For example, the same phenomena happens also for the quarks. But you see, the problem here is, let me say, not the problem. Since they are moving relativistically, their masses are very small, let's say, the oscillation frequency is very small. So the electron neutrino stays as an electron neutrino for kilometers almost. But for the quarks, you can deal with the quarks with the same scheme, let's say. The oscillation frequency for the quarks is even smaller than the size of the proton. So in the case of the proton, this oscillating term just causes our more trouble. So we basically stick with mass eigenstates all the time. We don't use the flavor eigenstates. For neutrinos, since they stay as neutrinos for kilometers, we stick with the flavor basis rather than with the mass basis. Well, of course, then we have this oscillation phenomena that we need to take into account. But if you do experiments in accelerators with neutrinos, they don't oscillate within accelerator, within the size of the accelerators. So it's, for us, it's easier to work with the flavor basis. Well, you see, I have two different kits as my basis. My Hilbert space is two-dimensional. Instead of one basis, I can use another basis. And we had already seen that this change of basis is due to a unit. We can write this change of basis as a unitary transformation. Well, in two dimensions, the only unitary transformation you can write it has this form. This is the most general unitary transformation you can write. So basically, that is what I'm using over here. But do I know this transformation? No, I don't know this angle theta. That is also something that I need to measure from experiment. So in a sense, I'm basically just making a simple model of neutrino oscillations here. Yes? Well, you see, it's not a physical angle. It's not a real space angle. It's just an arbitrary sum. I mean, I know that this number squared plus this number squared is 1. So if you have two numbers there, if their squares are 1, then you can always write one as the cosine of some angle, the sine as the cosine of some other angle. It's the same angle. Well, there's no phase here. All the phases you can just eliminate in 2 dimensions. Now, in principle, you can have some phase over here, e to the power I delta, but by just redefining the phase of nu2, I can just ignore that phase.
Peki, kuantum kimyaların time evolution'a bakarken onları enerji eigenketleri olarak değil de mesela position eigenketleri olarak göster.
Well, you see, let's go back to our description. We know how the state, we can straight away write the evolution of any ket if we expand it in an energy basis. So if you want to find the time evolution, first express it in energy basis. Of course, you can make your life harder if you want, as hard as you want. But, I mean, what's the point? You can write first expand it in terms of position basis, and then you have to expand the position basis in terms of energy basis, and then you know the time evolution.
Peki bu nötrinoların state'lerini flavor basis değil de bahsettiğiniz mass basis'te yazsak
Okay.
yine aynı şekilde aynı sonuca ulaşacağız değil mi?
Well, you see, we are talking about probabilities here, but we have to also, we don't really specify what are we measuring, what are we observing. I'm saying that, okay, so you create an electron, neutrino. So how do you know that it's an electron neutrino? Well, we see the electron that is moving, that it has interacted with that neutrino. That is how we can determine whether it's an electron neutrino or some other kind of a neutrino. And then when that neutrino moves some distance, if I want to measure the probability that it stays as an electron neutrino, I have to look at it and see if it is still an electron neutrino. So I have to look at basically, at this point, I know that I should measure an electron, then I know that there is an electron neutrino created. How I detect these neutrinos, this neutrino comes, travels a distance, in my detector, it just creates an electron. It interacts an electron. What I observe actually are the electrons. So basically, I'm measuring an electron neutrino state and an electron neutrino state. So those are the things that I'm measuring. So that's why it makes more sense to talk about these probabilities. These are the things I can actually measure currently. If I want to measure the mass eigenstates, whether they change or not, what I have to do is I have to measure their energy very precisely. So that if I measure the energy very precisely, if I can measure both the energy and momentum, but I have to be very, very precise. In that case, I can say that it has definitely this mass. But you see, the precision I am talking about here is we know that the neutrinos, their mass differences are less than 1 electron volt. Well, take an electron, let it accelerate in a potential difference of 1 volt. Its kinetic energy will be 1 electron volt. Well, Einstein tells us that that corresponds to some mass divided by c squared, the speed of light squared. That is the mass differences between electrons. Those are the differences that we are talking about. So if you want to measure a mass eigenstate directly, we have to make sure that we are measuring the energy of this proton, energy of this neutrino very, very precisely. The neutrinos that we are able to measure have, the ones that have the smallest energy that we are able to measure currently has energy typically 1 kilo electron volts. That is 1,000 electron volts. So the precision we need is more than 0.1%. Well, that we cannot measure. Because if we can measure the energy with a precision more precise than 0.1%, in that case we can say what is the mass of the neutrino that we are measuring. But telling whether a particle is an electron or a muon is much easier. So currently that is what we are able to do. So we can measure the flavor of neutrinos, but we cannot measure the mass. We don't have that precise equipment yet. And by measuring the flavor and how that flavor changes as a function of this L/E ratio, we can determine the mass differences. Well, you see, this is nothing but the interferometer that you see using light. Or how, for example, Michelson-Morley made this experiment, and he saw that the speed of light doesn't change with direction with the velocity, speed of Earth, or the direction of the speed of Earth. So he wasn't able to measure the speed. I mean, he wouldn't be able to measure the speed of light very precisely, but he can nevertheless measure the changes in the speed of light. Now, this is basically the same idea. We cannot measure the mass of the electrons, neutrinos yet, but we can measure the differences in the masses very precisely. Now, let me just say one more thing, and then we will continue next Monday. You see, look at these terms. Theta is just a constant. These do not change. So you are basically creating a state as an electron-neutrino state, and you are looking at the changes in it. Well, look at this term. The change will be significant. The initial state changes significantly. It can change significantly from its initial value if delta E times, let me put delta T, is h bar. So after this much time, let's say, the state might change significantly from what we had initially created. Well, on Monday we will see that this relation is quite general, not specific to neutrinos. In general, if you create a state that has a spread in its energy given by delta E, and that state will change in time, and that change can be significant only if the time that passes from the initial time is of the order of h bar. This is in general for an arbitrary ket. This is what's called the energy-time uncertainty relation. Well, first of all, as you see, this is not derived using some operator commutation relations. Time is not an observable. Time is not an operator, let me put it in this way. Aren't we observing time? So how come it's not an observable? How do you measure time? How do you measure time? I don't see any extra dimensions. How do you measure time? We have our watch, right? We are measuring time. But what are we actually measuring when we are looking at our watch? We are looking at the change in the position. We are not measuring time directly. We are not observing time. Or we use some kind of a pendulum. We use some candles. We are measuring the position directly, or are we? That's another problem.
Olaylar arasındaki, yani daha doğrusu bir durumdan bir duruma geçmeyi time evolution olarak gördüğümüz için.
Yeah. So we are looking at changes in the state and interpreting that as time evolution. And from that we are deriving time from other observations. So that's probably why we don't have a time operator. Well, it becomes problematic though when you are doing relativistic physics. Because as you have pointed out, Einstein just tells us that position is just like time. They mix if you go from one reference frame to another reference frame. So we will see when we write Schrödinger equation, even now when we are talking about time evolution, we are treating it differently than translation, for example. Time evolution turns out to be different. Well, which is kind of not nice. It doesn't play well with Einstein's relativity. So this is not a relativistic version yet, let's say. We did manage to write a relativistic version of quantum mechanics, but it turned out that rather than promoting the time to an observable, we have demoted position as a parameter. So we don't have a position operator now in relativistic quantum mechanics. It's just a parameter. Then comes the question, are we actually measuring the position? Okay, we always like thinking that we are measuring the position of objects. But, well, if you think of it, most of the time what we are looking at, we look at some position, we are not measuring the position, and we are trying to decide whether something is there or not. Right? Do you agree? No, not really. I mean, we can talk about position, but it's a parameter. So you just give me some numbers, some parameters. I look at there, and I see if there is a particle or not. I'm not actually, well, at least in the relativistic approach, I'm not actually measuring the position. I'm just looking at that position and telling whether there is a particle there or not. So that's not a position measurement, though. So that's basically what we do in relativistic quantum mechanics. Anyway, so that's all for today. Any last questions? I hope I have left you with many questions. Well, you see, this is not an exact equality anyway. So if it's typically of the order of h bar, well, h bar over 2 is of the order of h bar. Twice h bar is of the order of h bar. They have the same order of magnitude. At least with this perspective, let's say, with that expression over there, I don't see any motivation in putting a 1 over 2 or a factor of 2 over there. But as I said, twice h bar has the same order as h bar. It has the same order as h bar over 2. It is definitely not 100 times h bar. Okay, so see you on Monday. And okay, not this weekend, but next weekend is our makeup.
Yes.
Is the makeup time okay with you? April 1st is our makeup date.